Welcome everybody to the Southwest Florida Tech Net. This is a weekly net that is sponsored by the Southwest Florida Tech Team, which is a new club starting out here in Fort Myers. Tonight we have a lot of topics. We have two main ones, and then during those two main ones we will have is Lee here?
Yes, he was.
He was?
I saw him.
You saw him? I see him.
Yeah, I'm here.
All right. Yes, I can see you and you're here. All right.
The purple shirt.
Yep, I see you. Whenever it's in just a second here, we will I'll turn off the screen share and then you can start your screen share on your end. And that's how you can do your presentation. So this week we have two topics. The first one is NanoVNAs. NanoVNA is an antenna analyzer, and they're widely used by a lot of people, but they're kind of complicated. So we actually have Lee here, N4WYE, who is going to give us a presentation on how to use these. And I'm really excited for these because I have one borrowing from Ian, and I can make it work, but it has a lot of stuff that I don't know how to use. So I'm really looking forward to this. And these devices are relatively cheap, so if you're looking for a good analyzer, it's sort of the Baofeng of antenna analyzers, kind of. So this presentation is going to be really good, I think, for everybody here, because these devices are somewhat complicated, and this will be great. And then the second topic that we have is amateur television and cool amateur television things. So amateur television is where you transmit live video over radio waves using analog systems, not like digital, FaceTime, Skype kind of thing, but actually transmitting it directly, sort of like over-the-air TV, exactly like over-the-air TV. And I've put together some little projects I've done with it and some information about it together. So that's going to be the second topic. And then after that, we're going to go over, we don't have really any news for this week. I know of a few things that I may just speak about, but we don't have any main things to discuss. And then of course, we'll just have the outro sort of slides after that, where we talk about the repeater and the local nets. That's the other thing. I'm going to talk a bit more in depth about some of the local nets that happen, because we do have some information in there about them, but we're actually going to make it a little bit more detailed. So without much more than that, I'm going to go ahead and turn it over to Lee. If you want to start your screen share, you are welcome to do so.
First of all, thanks for the invitation. And I've got a slide deck here of about 30 slides. How's my audio, by the way?
Very good.
Very good.
Okay. I'd use this thing because it cuts down on the echo quite a bit. And I just wanted to make sure it was running out okay. Anyway, I'll go through the deck fairly quickly on the things that are just, of minor interest here. And I'll try to focus on actually the operational side of it. Since some of you already have it, then that's where the focus is. I'm retired and living in Atlanta, actually in Marietta. And I started my ham career in Hawaii in 1957. And if you remember the sunspot cycles, 19 was probably the best one we've ever had. And that's when I got my license in Hawaii. And thoroughly enjoyed it. But like a lot of us, backed away a little bit during the work years and got back into it here in Atlanta a few years back. We retired to Hilton Head and decided the alligator in the backyard wasn't exactly what my wife had in mind. So we moved back to Atlanta. But in any case, I'm one of the founding members of the Raleigh Amateur Radio Society. We started that thing in '69, and I built the 0464 machine in Raleigh, the original 0464 machine. I've been in the high-tech industry for 40 years. And let's see here. Let's see if I can't keep this thing going here. Here's the outline. I won't go through it in detail since we got some more people here online. When I got here, I got back into ham radio and I thought, I really probably ought to start with my antennas. get a good software-defined radio, play with my antennas before I decide what to do about an amplifier. And I live in an HOA, and that's my antenna farm I've got up right now. I've gone through about probably 10 antennas total. Started out with the off-center fed, the red off-center fed dipole, then got into the in-fed half wave activity. You see there a pair of orthogonal in-wave, in-fed half waves. And then I just started with a 40-meter loop, and I'm pleasantly surprised at how well that's doing. The in-feds are at about 65 feet. The 40-meter loop is about 40 feet.
Wow.
I've got good oak trees to work with and a decent slingshot, so I can get them up there. The only problem I've got is I hope my wife doesn't see all the fishing line hanging up there during the winter time.
You must have done this just recently then.
It's in the last couple of years, yeah. A couple years ago, I was at one of the ham conventions, and I started looking around for an antenna analyzer to work on the antennas. And I thought to myself, maybe I'll just hang tight. I don't want to spend $300 on one.
Wow.
And so I thought, okay. Then the VNAs came along, the NanoVNA-Hs, and basically I got into that. And it turns out, most of you probably already know it, but it turns out that it's a much more useful device than an SWR bridge or something like that, because you've got both a reflection mechanism on a single port, but you can also do transmission or through measurements. And when I build the LDMOS amp, I'm going to use this thing to tune the filter with on the output stages. But basically, a network analyzer, a vector network analyzer, is used to characterize RF devices, and it's been around for a long time. Here's a spread of what you'll see out there. The one on the left is about 50K on the used market.
Wow.
And the middle one is, a ways towards the $60 one. But I think the conversion, if you think about it, it's software-defined radio technology and software and firmware capabilities and some of the integrated circuits that this thing's really not that complicated. And it just took somebody with the vision of saying, hey, how do I take what I know about firmware, this hardware platform, and do something useful with it? And I think it's been an interesting journey. If you look inside the device, this is what it looks like. The DUT in the middle up there is a device under test. So it's whatever, if you got an antenna plugged into it or an amplifier plugged into it. But basically, it's a bunch of splitters, sources and receivers, and then digital signal processing. And the digital signal processing here is the same sort that's used in your cell phones, pretty much. So it's nothing really fancy if you know the rest of the technology field out there. But if you look at it, these are the kinds of things you can do with it. If you take just the standard reflection stuff, single port, plug an antenna into it, certainly SWR, you can look at the load impedance. You can look at power splitters and diplexers, filter return loss, amplifier return loss, cable impedance, feed line length and distance to a fault. If you go through, you can look at filter measurements, look at balance, do phasing networks and amplifiers, and it becomes a much more useful device.
Repeater duplexers wouldn't be good for
I'm sorry?
that. Repeater duplexers.
Well, you can tune a duplexer, but the problem is you got limited dynamic range on this thing. And the real question is, if you're really trying to get isolation that you need in a duplexer, question is, do you really have the dynamic range to do it? I'm not sure you do.
Yeah.
Because if you think about this thing, it's got a source in there up to 300 megahertz, but to get to 1.5 gigs, it uses harmonics. And so the harmonics are not the amplitude of the fundamental. And as a result of that, you end up dropping. You'll see later on, the dynamic range drops down in the 30s and 40s dB range instead of 80 or 90. that I think you need for a duplexer. But anyway, it's the geek toy of last year, in my humble opinion. And it's like an RF multimeter. And for $60, it's a lot better than a multimeter. Although I think the old Simpson 270s are selling for about $60 now. This is the one I bought on Amazon, and I took a shot and said, okay, I know it's a Chinese clone. I know I could get bit, and I thought, okay, I'll just pay a little bit more for it and go through Amazon and take a shot at looking at reviews and things like that and see what I can do, and ended up getting a good one. So this is the one I've got. This thing, a little bit of background quickly. This started out as a kit in 2016 by a guy named Eddie 555. And he was a design engineer type and had some starting points that some hams have already started down that path. And he just kind of started with that as a base. And then the cloning started off. And then a guy named Hugen 79, who's done if you will, the launch of reputable NanoVNAs that you can buy and believe you're going to get a reasonably good quality product. And he's extended it up to 1.5 gig. And he's also taking the firmware up and adding features and functionality to it. So you got a firmware lineage to work with. And the one he's done looks like the leader of the pack in terms of software resources and what the open source software family or communities is supporting. As an example, the larger screens are already here. They're going to 3 gig. That's a slightly different platform just to get the noise performance up. They're going to be putting on the firmware. In fact, I think the firmware is already in trial now to do screen capture. Because one of the problems you have with this device is once you turn it off, you've lost the data. And unless you plug it into a phone, an Android phone or a PC, you don't have any way to capture the data except for using your camera on your cell phone, which is what I've done. And that works okay. I mean, how many of us would take a PC out to an antenna anyway?
Yeah.
Right. I mean, so this thing to me has turned out to be more useful than I thought. And a lot of the detractors who say, yeah, but it doesn't do this. Well, if you look at the new H4 NanoVNAs, that's the nomenclature for Hugen's 4-inch version of the 2.8 version, 2.8 inch I've got. The SD card connector is starting to come on the new ones. So you're going to be able to do a screen capture with an SD card, and the firmware is coming to support it. So the one last, I think critical feature is in the test side right now. Let's see. Okay, I'll keep going here pretty quickly. We don't need to go through the block diagram. Let's go towards the operational side. There's a schematic. As you can tell, for what it does, it's not a very complicated schematic. There's not that much there. It's basically ICs and bridges put in there. And here the specs on it. If you look at it, the current H4 model goes to 1.5 gig, gives you a 0 dBm output. You got 1 milliwatt output. You can move it around a little bit, but not much. The dynamic range when you start out for the first 300 megahertz is 70 dB. That's pretty good. But if you look at the top end and when you get up to starting to tune, some of the stuff you'd like to tune up in the higher frequencies, you're getting down to 60 and 40 dB dynamic range. So it's a little touchy up there. Mm-hmm. You got a USB interface on it. It's an internal battery. The battery lasts about 2 hours on mine. So it's halfway decent. You've probably heard about the 101 points, not enough points. You really can't get, the detail you want. Well, you actually can. The newer versions of the firmware are starting to come out and have more points on it. Like 400 or something like that. And that's going to continue, I think.
Oh, wow.
But if you look at, let's say, your HF antenna and you go from, let's say, 50 kilohertz to 30 megs on one screen, the problem with the 100 points is in the 40-meter band, there are only 2 data points you're going to get data on in the whole 40-meter band. So that's the problem with the 100 points, because you got a wide screen, you're covering 30 megs, and the bands are pretty narrow. But if you go from 7.0 to 7.5, you got 100 points in the 40-meter band. So you don't need to worry about the fact that it only has 100 points, because you can just, get the microscope out and turn it down to, 500 kilohertz bandwidth or width, and you got 100 points in that 500 kilohertz. You got 4 traces, 4 markers, and 5 memories on the existing unit. And it's nice and stable. You can use it as a signal generator. It's stable enough to do that with.
Wow.
You may hear the term S parameters, and we'll talk about that a little bit just to give you some understanding of that if you don't have the background. But S parameters are what they call scattering parameters. And it's the same sort of thing of, let me get into it a little bit here, but let's do this first. Here's what the unit looks like. And by the way, here's what mine looks like. There it is. It's got a plastic case on it. Okay, and there's the connector. But basically, if you look on the left-hand side, one of the things that scares a lot of people is that when you first turn the unit on, here you are, a new proud owner of something that you feel like's a good deal, and the screen looks like that when you turn it on. So it scares people. It's like, I got a bad clone. Well, what happens is those are just receivers and sources turned on, and all the screens lit up so you can see everything. And that's noise. A lot of the cyan colored trace there is just noise in one of the detectors. So that's just what it looks like when you turn it on, but don't let that frighten you. If you look at the controls, you got a USB port, power LED, power switch, a system LED gives you some idea. And then you got a rocker wheel on top, which is a little tricky, but you have a touch screen and you can use remember your old Palm Pilot stylus? You can use that kind of stylus on this, or you can use a pencil or whatever you want to. It's not a real easy touch screen, but you can do it. Problem is, on a 2.8 screen, your finger's pretty fat. Yeah. But if you look at it, these are the 2 main screens you see pop up. The first one there, you'll notice it goes, the bottom part of it, you can't read it, but it goes from 4 megs to 900 megs on this particular one. And on the right-hand side, you see the beginning of the menu. The displays shows you traces, formats, scales, and channels. Then the marker, you can add markers, you can make them a particular function, and you can search for markers. On the stimulus, you can put the start and stop, like on the beginning of the band and the end of the band, any frequency range you want, or you can put a center of the band and put how much span you want. So you can do it either one of the 2 ways. Then there's a calibration mechanism. You've probably heard bad things about the calibration one, but don't let that scare you, because all they're trying to do is to take out all of the variables and make sure that the readings that you get are accurate. I haven't calibrated mine in probably 6 months. Okay, I just use it like it is, because I'm using 50 kilohertz to 30 megahertz. And so I've calibrated it for that frequency band, and I haven't noticed any problems with the accuracy at all. And I've done the calibration over again, and it's dead on. So I haven't worried about it. The screen down here below shows you how to enter numbers and multipliers and things like that as you're putting frequencies in, stuff like that. But that's a user interface. It's really not tough. There's a little learning curve, but once you learn it, it's not a big deal at all. For instance, if I want to do SWR, I turn mine on, and it goes to that screen, and there's my in-fed antenna. So it's set up, it's calibrated, it's ready to roll, and I got it on 3 to 30 megahertz or 50 kilohertz to 30 megahertz, and I put that in memory and calibrated for it. So whenever I want to use on one of my HF antennas, I don't have to calibrate. I can just go directly into the measurement, and I've got it set up for SWR measurement when it turns on from scratch. So there's the menu tree of walking it through the menu, but this is a software guy's version of how it works. It's not how to measure SWR. So you have to know how to walk through this thing. But basically, this is the diagram that would allow you to walk through doing a measurement that you might want to do and show you how to get to it if you get stuck. Let's see here. Before each set of measurements, you need to configure the VNA by what kind of traces do you want. If you're doing SWR, you only need one trace for SWR. You got 4 traces to work with. What kind of format do you want? You want SWR? Do you want return loss? Do you want a Smith chart? You know, what kind of format would you like to see the data in? Scale, you can set the scales so that, you know, if you want to see details of SWR, you can move the 2-to-1 line and 3-to-1 line up and give you some more space to see what the scales are. So they're all flexible. On the stimulus, you set the frequency range and then the calibrate. Can you see my marker, my cursor?
Yeah.
Oh,
yeah.
This is an absolute gem right here. It's on the references at the end of the slides. But this guy did a super job of taking a beginner's guide to a NanoVNA and writing it down in whatever detail you want to go into. I'll hang tight for just a second. I want to write it down.
Absolute Beginner's Guide to NanoVNA, Martin's Faco.
I think the guy's from Slovenia, I believe, but he did a wonderful job on it. Okay, here's the calibration side. And basically, if you look on the left-hand side of the screen there's a bunch of letters, and I put them on the left side of this screen right here. And they are right here on your screen. Oops. Let me back up here. They are right here. And basically, there's a little trick here. Notice that's a capital C. That says it's calibrated for the frequency range that you're using. If you go to a different range and it's not calibrated, that goes to a lowercase c.
Oh.
Okay, so it'll tell you if it's calibrated for the range you're using. All right. And then basically, these are the kinds of things that you're measuring: directivity, reflection, source, matching of the source, transmission tracking, and then isolation. Those are the kinds of things that you go through with an open, short, and load on the port as you go through it. And you put them on one at a time and just walk through the menu, and bang, it's calibrated. And the basic idea here is if you look at a Smith chart, for those of you who know Smith charts, you know that a 50 ohm point that's purely resistive is right in the middle of a Smith chart. Okay. And so they're trying to make sure the cursor is sitting right there. And then on one side of the Smith chart, let's say over here, it's either short or open. And on this side, it's either open or short. I forget which is which. Okay. All right. I'll hit the right button here in a minute. Oh, what's that? Can't tell why it's doing that. I'm just going to step it through manually here just to make sure. Okay, here's an SWR measurement. This is what the screen looks like. We'll walk through it real quickly. See, it says SWR.
Mm-hmm.
Scale of 1. This is 2 to 1. This is 3 to 1. and that's 4:1. So the scale is one scale, one integer of SWR is one line up. Okay. You can change that and make it a quarter if you do. You want to make this a quarter, a half, 3/4, and SWR of 2:1, you can do that. But right on this one, this is 1:1 on the bottom. This is an in-fed half wave antenna, and this is 2:1. Okay, so it's a pretty decent performing antenna. I've come to love those things. I've built the 49-to-1 transformers and I like it a lot. One of the only problems I had with it when I put it up was I put it up at 65 feet and I didn't want to take it back down, and notice my resonant point is at 6.9. So it's outside the 40-meter band. But as it turns out, it didn't matter because the SWR is still low enough that 7.3 was not a problem. Okay, but here's the frequency of the marker. Okay.
That's what a little arrow is.
Yeah, there's the arrow right there. Okay. And this is the starting point on this side of the screen at 50 kilohertz. And this is the end over here at 30 megahertz. So you can see there's a 40-meter spot right there. There's 20, 15, 10.
Oh, wow. Now that's really nice.
That shows you the.
And so, it shows you a lot in one chart. And now you want detail. Okay. Let me take this chart to the next step. All right.
You must have an 80-meter in-fed half wave. Is that right?
Let's see.
Is it 130 feet long?
I don't remember which one this was now that I think about it. I had an 80-meter, but I didn't think this was it. Okay, here's
because you've got low SWR points down below 7 megahertz.
Right. But I think that's the answer is I don't know for sure.
Don't let me sidetrack you.
Now, let's see here. This thing should be running. What I wanted to show you here was a little bit about how to interface with the screen. Okay. And in just a minute, you'll see it come up.
You can see
the video is running.
Yep. Yeah, we can see the little lines wiggling.
Yeah, basically, let's see. Can you see that note coming up on the bottom of the screen?
Yeah, I see it. I have two.
Okay.
My NanoVNA.
Then I got to figure out how to put that screen back where it's supposed to be here.
Better.
Yeah.
I've gotten it out of the play mode somehow, and I just don't want to take a chance on screwing it up. Okay.
That looks good.
All right. Okay, you see it wiggling a little bit right here.
Yep.
So the video is running, and the idea here is basically to show you what it looks like as you start to use the device. Okay, it'll show you what the menu screens look like as they come up.
Right now, there's only one. What is that? So the little lines at the top. Yeah, the marker. There's only one marker.
There's only one marker. Yeah, I didn't put a bunch of markers in there, but you can put them in there. Now I wonder why. Oh, here it comes. Okay. Now I'm recalling what I did is this is a plot of return loss. For some of you who know what return loss is, basically it is the loss of the transmission towards the load and how much of it returns. So it's return loss, if you think about it that way. Okay. And this is 0 return loss, and this is now 10, 20, 35 dB return loss. And that's, see where the SWR is down here?
Mm-hmm.
This is 7 megahertz right here, by the way. This is 6 over here, and this is 8. So there's the 40-meter band. Now we'll go to 20. Okay. You can see, though, you get a much better idea. You get more precision with return loss than you do on SWR on the previous chart and on some of the others. You get a better idea of where the real resonant point is.
Oh, yeah, there are more steps in there.
The one you saw before had a lot more detail to it. The next one's going to go to 15. But you see how you take the 30 meg slot. I put in 13.5 to 14.5. And on this one, I'm putting in, let's see, 20 megs to 22 megs. We'll see how deep that notch is. You don't see that on the SWR so much, but this gives you a better idea.
So down, so when it's going down, that's more reflection?
No, that's less reflection.
Less reflection.
That's like 1% reflection there, right? Just like SWR. When it's down like this, that's less reflection.
Yeah.
Okay.
So it's negative 40 dB.
Right.
Okay.
And you want to make sure you got at least 15 or 20 dB on a resonant point that you're trying to use. Otherwise, the Q of your antenna is not high enough to do you a lot of good. And here's 10 meters. So it gives you, look at this antenna. That's 1.6 to 1.7 covering the whole 10 meter band. And you just saw an end-fed that covered everything I wanted to cover. Frequency-wise, I didn't have to worry about CW versus sideband on 75 or 80 because I chose to do a 40 meter antenna. And I just moved it up a little bit so I could get the whole 10 meter band. Now here's a Smith chart. Okay, remember I said 50 ohms is right in the middle? Yeah. There's 50 ohms right there. And notice it says basically 49.8 ohms and 1.65 nanofarads. So that's the actual impedance right there on that antenna. And 1 to 3 is the same as 1 to 3 here. So that is the frequency of 28 to 29.7, I think, or something, wherever the band is up there. So that gives you an idea what a Smith chart does for you. Okay. Okay, so there's that one. Now let's move to the next one. Bartley, I'm sorry if you can hear my dog. I apologize. I'll try to quieten him down. He has one of his toys he's playing with, and he's decided he's going to be my friend for the night, I think. Okay, on this one, let's see.
Is that the same clip, or is it?
No, it's a different cut at it.
Oh, okay.
Okay. The answer was I was on the same one, and I didn't mean to be.
Oh. At the end, are you going to be available for taking questions?
Oh, sure.
Because I know I have
not a problem at all.
I'm going to have a couple.
Okay. All right. And on this one, the idea here was to walk you through setting these screens up. You want to set a set of, let me back, well, I don't know if I could back it up without screwing it up. So stop. There's the 8 megahertz side. So you see that goes from 6 to 8. So I just changed the scale by tapping on the screen, and I can move the cursor around and look in the upper right-hand corner. You'll see where it is.
You can also use the little rocker switch on the top to go up and down, right?
Yeah, you can do that. But it's easier to me. I found it easier to put a pointer on there because you know, getting the marker on the right spot, because the marker has got multiple dimensions to it, not just rocking, but up and down as well. And I found it difficult to manage it. And there's a noise here, and I'm moving it over, moving the detector over and changing the channel, showing the reflection. There's the return loss. Okay. And again, you get a much better idea of where the resonant point is. So
wow, that's really.
Yeah, it's a lot more precision. And you can move it around and find out where it is. There's a 6.980 you saw before on the end-fed plot. So that's one way you can use it. And here's again is the Smith chart, and you can actually move this one around as well. You can take any one of those 3 cursor markers, put the cursor on it, and the others will move with it. So you can see the impedance going down to 45 ohms. Okay, so there's that. Here's my off-center fed antenna, and that's what it looks like on 80, 40, and 20. Again, using the same sort of methodology I just showed you on the screens. Here's a 40-meter dipole. You can see the real high Q dipole, and there's 15 meters. And there's 40-meter right there, Smith chart version of 40 meters. Okay. See, it's above 2 to 1 at the band edges. That was my attic antenna, the first one I put up, by the way. Here's taking a look at that end-fed, the SWR numbers that we just saw. Remember that 6.9? That was 1.09 SWR. And if you look over here, here's the ICOM 7300. And you can see it coming down at the bottom end of the band, down to, approaching 1 to 1. Okay, so this is a comparison of what you see here and what the 7300 SWR graph showed. Okay, so there's covering the whole 10-meter band, and it's below 1.5 in the whole 10-meter band. And there's 20. There's no, it's 15. There's 20, and there's 40. Okay, let's see. We don't need to go through that one, I don't think. Here's an interesting one, by the way. I got into looking at delta loops. As you can tell, I'm moving from an attic dipole to end feds to off-center, actually off-center fed next, end feds, and now starting to look at loops. This is probably, I did all these measurements in probably about 15 minutes. Okay, so I'm outside of the antenna. I'm looking at it from 50 kilohertz to 30 megahertz, and that's what you'd expect. there's 20 meters right there. Okay. Then if you look at it 13 to 15 megahertz, there's 20 meter, and 14's right there, okay? And then you look at the Smith chart, you can tell that, okay, it's not at 50 ohms, but it's not too far out of whack, but it's higher impedance than 50 ohms. So you got to move it back to the left. So I used a matching section, a 75 ohm matching section. And then I thought, okay, how do I know how long to make that matching section? Because I don't even know the velocity factor of the coax I'm going to use to do it with. Because I had a chunk of a 75 ohm CATV coax, and I had no clue what it was like. Well, I hooked it up to the VNA and basically moved the frequency around to the frequency I wanted, and then started cutting it. Okay, and it was sitting up here, and I started cutting it, and I went back here, and I'm halfway around the Smith chart. Okay, well, that's a quarter wave stub. Okay, by definition. Okay, so I was able to use this thing and get by having to figure out what all the numbers had to be, because I didn't know what the coax was, and I didn't want to go buy a piece of coax. So looking at the matching section, you see the 100 ohm point here, it is now at 50 ohms. So I actually took the NanoVNA off the antenna and went to the end of the matching section, not in the shack, but at the end of the matching section. And you can see it sitting right there at 50 ohms. Okay. Notice the SWR. Moved, and you get a better sense of what you're looking with here as well. And if you go inside the shack, here's what it looks like. 50 to 30 megahertz. And it's a 20 meter antenna, so there it is. And there's what it looks like inside the shack. All right, the SWR is a little better because I got some loss in the coax, so it naturally looks better. That's really what the impedance is right there, SWR. And there's the Smith chart right in the middle again. So there's an example of taking an antenna at the antenna itself, putting a matching section or something on it, could be a tuner, could be whatever you want to have on it, and then going in the shack and measuring it. And I did all that in just, not very long at all. So that's the quality of stuff you can do with these nano VNAs. You can also look at filters. Here's a 88 to 108 band stop filter. Get rid of FM noise if you're using an SDR kind of receiver. You might get overloaded with a strong FM station. So here's the notch to get rid of it.
Wow.
And if you look at here's what the Smith chart looks like, return loss, and anything else you want to take a look at. But if you look at this right here, the middle of the passband, that's I think I can't read the number, but yeah, it's 96 megahertz. I got to get back again. Sorry about that. I got excited. Okay. Another thing you can do is if you want to look at your 2 meter or 6 meter or 432 antenna, you can actually take a piece of coax, take the VNA, get outside the near field of the antenna, rotate the antenna, and plot the pattern of gain on the antenna.
Whoa.
Okay.
Yep. Cool.
Because don't forget, you got two connectors on this thing. One's the transmitter, one's the source, and one's a receiver. Okay. So you put the antenna in the middle, and that's a plot of it right there.
That's really cool.
Here's a time domain reflectometer. If you got a 100-foot tower and you want to know where the break in the coax is, you can find it before you go up the tower. Okay, I won't get into this one, but NanoVNA Saver is a software package that goes on the PC, and you can hear the screens. You can see where you can separate the screens. You don't have one overlaid on the other. So that's the advantage of this. You're not limited to 100 points, so you can get a lot more detail. And you can basically, here's the set of features. I won't go into them a lot because, to be honest with you, I haven't found it necessary to go find a PC and hook it up to do this, because I can do what I want to do with it. And I've gone through about 8 antennas now with it. So I haven't found the need to go do this yet. But it's good software. It's easy to operate. It's as far as I know, it's open source software.
Yeah.
Okay. Here's some useful sources and links that might be helpful. And I'll send this. What's an easy way to get this to everybody?
If you put it in the Zoom chat.
Easy for you to say.
Yeah, there you go. I wonder if that'll work if you just pop that whole thing in there.
Well, I'm on a Mac, so it probably will. I'm kidding you, PC guys.
Gosh, I was gonna start saying some things.
Let me find chat up here. Where'd it go?
When you're sharing the screen, it's kind of hard to find it. There we go. Well, that worked great.
Okay. Now you know why I use a Mac. Okay.
Yeah.
All right. So anyway, here's an introductory video that's pretty good. But there's 10,000 videos out there now, and you can find a lot of them. There's a Groups IO forum out there. This again is the one I told you about. He's on version 1.6 now of this, and so get the latest one. The H4 is the only one to get right now, I think, if you're going to buy one. And here's the guy who wrote the software for the NanoVNA Saver. And here's an introductory chart for a Smith chart if you want to, get crazy.
I probably need to watch that.
Well, it's useful. It's useful. Okay, let's see. Where am I here? Yeah, here's the wiki and the groups IO stuff. You'll notice there are two VNAs on here. One is the one you'd expect, and here's a new one. And this one goes up to about 3 gig, but it's a different platform altogether. But if I'm not mistaken, the firmware coming out supports them both. Don't quote me on that because I'm not sure. There's lots of YouTube videos out there. And basically, you know, the NanoVNA is really a powerful RF tool. It'll do most of what that $50,000 machine will do. Maybe not as well, but well enough for what we're trying to do with it. It's an open architecture on the software side. GitHub is the repository. And by the way, my daughter-in-law used to be the privacy lawyer for GitHub.
Oh, wow.
And by the way, here's the source that I would recommend, and that's RNL. Everybody I know that's bought one from RNL has been satisfied with it, and these guys will back it up from what I've seen so far. The 2.8 inches, $60, and the 4 inches is $90. If you're going to buy one, I'd buy the 4-inch. This screen's a little bit small, but it does get the job done. If you're going to buy one new, I'd get that one. And by the way, here's my azimuth plot of the results of all my antenna work. This is a plot of showing 20 meters, the loop versus the end feds, which are orthogonal. Okay, so I cover basically pretty well any azimuth I want to. And if you look at this is measured in S units, 1 S unit, 2 S units, and 3 S units. And you can see the loop will beat the end fed facing Europe by 3 S units. And the end fed is 25 feet higher.
Are these standard S units like you would see on a radio?
Yeah, these are like 6 dB S units.
Yeah.
I call them 3, but this is really, let me back up. This is what I did was, this turned out to be, it's a lot closer to 6 than 3. Okay. Because I had to interpolate a little bit given the ICOM 7300 that I'm using to get this plot right. So it's kind of part way, but it's a lot closer to 6 than it is 3. But you'll see that only in certain areas did the end feds even get close. And that's only 1 S unit difference. So I turned out to be a loop guy.
Wow.
I couldn't believe it. Now on 40, it's not quite that one-sided. It's more even than this looks on 40 meters. Okay, I got a test question for you. Now that you've gone through the thing, I want you to tell me what kind of an antenna that is. The other 4, by the way, just a heads up, the other 4 clubs that I've given this presentation to got the answer. Okay. Let me know if you want a hint.
Don't tell us that. I'm.
All right, think about a Smith chart for just a minute. Remember 50 ohms is in the middle?
Mm-hmm.
Notice that antenna goes from 50 kilohertz to 900 megahertz and it stays close to the middle.
Sounds like a dummy load to me.
Nope, dummy load wouldn't do that. Dummy load would be a spot in the middle.
Oh.
Discone?
That's it.
I'm going to say discone.
Yeah.
Wow. That's really impressive. I didn't expect the discone to actually be that stable.
Look at the SWR curve. I didn't either.
I know. That's amazing.
Wow. I'm about to build one for VHF here.
That was the first antenna I put up in the attic was a discone because I didn't have enough time to get the dipole up. And so anyway. Okay. Any questions? I hope I didn't run too long.
No, you were perfect. I have a question. Let me open it up to anyone else who has any questions for Lee. Anybody else have any? If not, I'm going to go ahead and ask mine. All right, I guess I'm the only one with questions then, which means you did a really good job. The main question I have is if you so you were mentioning calibration and it being calibrated for a specific band. I have a NanoVNA here that I am borrowing from Ian, and I don't have the calibration, the little ends that you put on it. I don't have those.
Okay.
And I believe it was calibrated once. So I mainly use this on UHF, but if I put this on another band and it hasn't been calibrated for that band, am I going to get highly inaccurate readings?
The answer is I don't know, but let me give you a way to mitigate that. Have you got a dummy load that's good?
I don't have any dummy loads. I need to get one.
You need a dummy load.
I know I need one.
Go buy a carbon resistor at 51 ohms. Okay. And make sure it sits in the middle of the Smith chart, and that's close enough.
Okay.
I mean, that's where you want your accuracy anyways at the 50 ohm point. If you're at 200 ohms or 300 ohms, that'll at least mitigate the problem, but it won't solve it.
So without the calibration being done, though, my question is, and how crucial is the calibration itself? If I use it in this state where it's probably never been calibrated, and I go take a measurement at 40 meters, and then I go take a measurement at 70 centimeters, are the results going to be, incredibly off from what they should be? Is it actually a reliable source of information without ever being calibrated? Because I didn't know you had to calibrate it for different bands, because you're saying you had different memories for different bands.
Well, you have different RF performance.
You have different.
Think about it. You're going from 10 kilohertz to a gigahertz and a half with semiconductors and a printed circuit board and splitters and all that stuff. To expect the same kind of noise performance over that band, you're just not going to get it.
No, I know.
Okay.
It's going to be wildly. I guess it's going to be.
And I think the linearity is going to be a little bit better. So it depends on you just trying to do SWR.
Yeah, pretty much. Just SWR, and then of course the impedance. Those are the two main ones.
I would before I'd trust it, I'd at least make sure on 50 ohms that you got a shot.
Okay.
Get a 50 ohm non-inductive resistor and try it.
Okay.
Okay. And then at least you got a first order approximation that it might be good enough to squeak by. Certainly you'll be able to tell, what the resonant points are on the antenna frequency wise.
Right.
So you can tell where minimum SWR
He can give you the calibration slugs.
Yeah, I think he lost them though.
You can buy them on Amazon and have them tomorrow.
That idiot.
Oh, now he's not here. You're going to trash talk.
You can buy them on Amazon.
Okay.
Yeah, I would trash talk him if he was here too. You know that.
Yeah. I need to get me the set of calibration points then, because I've been, especially when I try and use this up on the higher frequencies where it's more important. I've been using this, my antenna could be different from what the thing is the readings actually correspond pretty well to the MFJ analyzer that we have on the 2 meter band and below. It actually, the readings seem to be almost identical. So at least it's working pretty well for that. But since the MFJ reader we have doesn't go up to UHF, this is kind of all I've had. But since I haven't really calibrated it, I need to do that. Yeah, those 3 little pieces there.
Well, think about it. This one's an open. So you can forget about that. You don't need that one. Okay.
I could make a short, probably.
Exactly. You can make a short, but you need the load. You need the 50 ohm load, which you can use as a resistor. You don't need a 2 gigahertz resistor.
No.
Depends on how far you want to go up, and being non-inductive.
So the kind of resistor I need was what to test that?
You need a non-inductive resistor.
50 ohm composition resistor. Yeah.
Yeah. Carbon composition is good. There's some metal. There may be some metal ones you can get too. The another thing might be to go ahead and buy an SMT with no leads on it, and just mount that in a small connector. That would be probably the most accurate one, because that's what these things really are. They've got SMT components in those connectors.
Joseph, you might be able to go into the swap shop, in our swap shop, and find something like this. This is off a Bird watt meter. It's a 10 watt dummy load.
Yeah, something like that.
Yeah.
But then he's going to have the issue of trying to go from that end connector or whatever you've got down to that SMA. You can buy these little SMA dummy loads, and the open and the short off eBay.
You can buy the connector adapters easily.
So those aren't going to interfere with the readings, though, are they?
Well, the point of the calibration is that you can make them so they're not part of the reading, because you calibrate outside of that plane, if you will. For instance, a lot of people, let me show you something. One of the things that you need to have is what they call connector savers, okay? Because notice these things stick out a long way on here.
Mm-hmm.
These actually just come off.
Oh, so you have like a little. Oh, I have one of those.
It'd be like an SMA or something.
It's just like it's just a little. It
just
extends it by one.
Yeah, but basically, what happens is if you keep spinning the calibration pins on the connector that's in the VNA, you're going to take off the gold, because there's not much gold on there. Because if you put the calibration thing on there and spin it, it's a metal pin spinning in the female connector. So if you put these things on, okay, the gold wears out, you replace the $2 part. So that's why I put these on here, and it's really a useful thing. But I'm getting to your point now. Let's say you had 2 cables with end connectors on it, and that's what you were going to connect to. All right.
Okay.
You would do your calibration of your short and your load at the end of those stub cables.
And they could be
so then what you put on those cables
long,
has been calibrated into what the readings are.
Right. Okay, I get it.
Okay. So for instance, if you wanted to know what your antenna looked like at the antenna, if you do the calibration on the end of the coax going to the antenna with these loads, if you do the calibration out there, it'll read what the antenna shows you in the shack. Because you've taken that out of you've made that part of the calibration position of the device.
I see. So we're in a different. I see. Okay. I'm definitely gonna need to see some of these guides.
The videos are pretty good, and there's probably, I bet you there's 500 videos out there. So, if you want to know how to calibrate it, just type in NanoVNA calibration routine on YouTube, and you'll have 50 videos.
Yeah.
So
that answers my question pretty good.
Okay.
Put that in there.
Good.
Okay. So anyone else have any questions? Well, see, that's what I'm going to tell you what Ian says. He says, if you don't get any questions, that either means you did bad or you did good. But personally, I think you did really, really good.
I hope it's helping.
What in-fed half-wave antenna do you have? Just curious.
I'm sorry?
What in-fed half-wave antennas do you have?
I built them.
You built them? Yeah.
Well, let me give you one sentence that might be helpful. Have you ever heard of a Facebook page? The author's name is Steve Ellington.
Oh, yeah.
Okay.
Steve Ellington. N4LQ.
Yep. His page is where I got the details to wind the transformers. And
that's what I've done here too.
Yeah. I mean, they're really good. I wouldn't buy one. I wouldn't spend the money to buy one. I've probably got 50 toroid cores now, though.
I've got a commercial model from my antennas and then I've got one that I built.
Yeah.
Which is the 40 meter. I think the one that I built actually works better than the commercial model.
It wouldn't surprise me at all.
Yeah.
Wouldn't surprise me at all. The one thing I did have to do was I had to take a turn off the secondary for the high-powered version where you use the 52 cores.
Yeah.
The 352 cores.
Oh, you use 52 cores. Okay.
Well, you use if you're trying to get power on that MFED, if you want to run a kilowatt, you need the 43 cores. If you run 2 of them, they won't handle that kind of power.
Saturate. Yeah. Okay.
And but if you take 3 cores and stack them up, I needed to take 1 turn off to get the 10 meter SWR down.
Yeah. Okay.
But other than that, I did a straight copy of what Steve recommended. And I've talked to him a number of times. And I think you're right. You can build one that's better than what you can buy.
Yeah, I definitely think that now.
Yeah.
Because I built mine, and I've worked Croatia and all over the place with it during contests on phone and on CW. And it's just 20 feet above the ground.
Yep. And I run 100 watts. I don't run any more power than that.
Yeah,
I figured I'd spend all my time and money on the antennas first before I decided to go build an LD MOS solid state amp, which is my next project.
Yeah. I don't plan on building an amp. So I'm looking at getting me a hex beam, but that may be.
There's an idea.
Yeah. So
I'm in an HOA, so hex beam is probably a little bit something I couldn't do.
Yeah. You'd have to tell them it's an upside down umbrella.
That's my big umbrella.
Yeah.
I got to have an umbrella like that here in Florida with all the rain.
Clothesline.
Yeah, there you go.
Yeah. Or as the Brits would say, a washing line.
Hang some shirts from it.
Yeah.
There you go. Hang your underwear from it, and nobody will say a word.
Isn't there I think there's some kind of rules somewhere in America, but it says you cannot prohibit anyone from putting up a clothesline. So if you tell them that it is a clothesline, then they, even in an HOA, as long as they can't prove otherwise, then they won't be able to shut you down, because there's nothing that says they have to let you put an antenna up.
It's hard to argue with a 50-foot clothesline.
Yeah.
That's 12 foot off the ground.
Right.
I don't like my clothes. I haven't got stuck in the light. Yeah.
Why is your clothesline 60 feet in the air? Yeah, man, that wouldn't work too well, I guess.
That's so that it wouldn't be in the shade of the trees.
Yeah.
And the birds wouldn't mind it.